I'm Jonathan Aldrich, and today let's talk about structured control flow, sequencing, and selection. Early versions of Fortran and BASIC provided gotos as the primitive for control flow. For example, if x is greater than 0, then we can go to line 100. Otherwise, we continue on to the next line. This is an approach that's called unstructured control flow because the goto is the lowest level statement possible. It just says go to some other place. Unfortunately, code with a lot of gotos can be very difficult for programmers to understand. It's sometimes called spaghetti code because you have to follow a line of spaghetti from one goto to another to figure out how the program executes. Dijkstra argued in a famous paper that goto was unnecessary and harmful. He said it was hard for programmers to understand, and he observed that a small number of patterns, mainly sequencing, selection, and iteration, are sufficient to write the programs that are encountered in practice. Dijkstra won that argument, and modern languages, as a result, use what's called structured control flow constructs instead. Here, the program is expressed as a tree of sequencing, selection, and iteration constructs, usually in the abstract syntax tree of the program. Let's talk about Dijkstra, one of our programming language people. He was known, among many other things, for developing many of the logical foundations of concurrency. An example data structure he worked with is semaphores, which we'll cover in chapter 13 of the book. He also contributed a lot to the practical development of structured programming. Dijkstra received the ACM Turing Award in 1972. Fun fact, he's also the academic great-grandfather of me. A lot of the controversy about goto was tied to a few common special cases that it was felt goto was particularly useful for. However, language constructs were developed to replace these, enabling us to write the programs we want to write without using goto. An example is that goto was used to jump to the end of the routine when we're done. But we use return statements that can appear anywhere in the function to do that instead. Goto can be used to end a loop iteration early. But now, we use break if we want to exit the loop, and continue if we want to go to the next iteration of the loop. Sometimes goto could be used to return from not just the function we're at right now, but the surrounding function. However, non-local returns, as provided in, for example, Smalltalk, can do the same thing. Finally, gotos could be used to jump back to a transitive caller in the case of error, but exceptions provide that facility in most modern languages. Let's talk about some of the core constructs. The very simplest one is sequencing, basically something that imposes a linear ordering on statements. It's just the semicolon in most languages. One statement follows another. This is the essence of imperative programming, and in fact, it's really only useful in languages with side effects. Why would we sequence one statement before another if the first statement doesn't actually do anything? Selection is more interesting. The most simple selection construct is our familiar if-then-else. Again, the else clause may be optional. But it's pretty frequent to string a bunch of if statements together. And some languages provide constructs with an else if. So we can write if some condition holds, then do something, else if some other condition holds, then do something, else if, and so on until we're done with an else clause at the end. The Lisp language provides a more general cond construct, which has a list of conditions and then an expression to evaluate for each one of those conditions. If the last condition is true, then we know we'll always get some expression out of this. These conditions are typically evaluated in order, and the first one to be true is the expression that is returned by the overall condition expression. Another form used in functional programming languages is pattern matching. Pattern matching combines selection with binding variables in a pattern. Those bound variables then can be used in the corresponding branch that was selected. Patterns don't have to be disjoint. They're simply checked in order, and the first one that matches is the one that is chosen. In the example I've shown here, we match a list in various ways. We first check if the list is empty, and then if it's the singleton list, in which case the value x holds the one element in the list. We can also test for a list that starts with 1 and continues with the rest of the list, which will be in the variable x's, and we can have a default case at the end to cover everything else. Some languages check for exhaustiveness. Some languages make that exhaustiveness check optional. I would suggest turning it on because it's often because that's an error you don't want to miss. Some others don't check for exhaustiveness at compile time, maybe because their pattern matching language is too difficult to do this in general, but they'll signal a runtime error if no case applies. A related construct, but simpler, is the switch case in C, which basically tests against a bunch of different labels. In this case, the selection branches are statements, not expressions, and so we don't have to return anything. And so C makes a missing label a no-op. We'll discuss pattern matching more in Chapter 11 on functional programming. How can we compile selection constructs? Well, let's consider the following source code. We have three tests here combined. If A is greater than B and C is greater than D, or if E is not equal to F, then we'll do something. Let's compile this. In a language like Pascal that does not have short-circuiting, this might be compiled as follows. We'll load A and B, we'll compare them, and store the result of the comparison, typically true or false, or 1 and 0 likely in the representation of the machine, in a register R1. Then we'll load C and D and compare those as well. Then we'll use an AND operation on R1 and R2, etc. So this code is basically just evaluating all the pieces of the expression in the expected order. It's fairly straightforward, but we can compile things more simply and do less work in a language that has short-circuiting. So let's look at how that might work. In this case, we're going to be using a compilation technique called jump code. Here, on the right-hand side, we load A and B, and then we test if R1 is less than R2. If so, then the first clause in the AND has failed, and we'll jump to the other part of the OR, which will be at label L4. Otherwise, we continue with the AND, and if we discover that C is in fact greater than D, then we'll go to the then clause because we found out that we're going to do the then part. Otherwise, we continue at L4. So this code is shorter, and it also executes fewer statements at runtime. That's one of the benefits of short-circuiting, and it illustrates the nice techniques of jump code. Note here that in the original code, in Pascal, Booleans are computed and they're held in registers. Whereas in the jump code, Booleans are represented implicitly as jumps. And that's what makes this code shorter and more efficient. Let's talk about strategies for implementing case or switch. The example on the right shows a case construct in the Ada language. It tests some potentially complicated expression against a number of different values. The first case would be if the expression equals 1. The second case tests for whether it's 2 or 7. The third case might be for a range. Is this value in the range of 3 or 5? We can test 10, and then we can have a generic clause for other values. Depending on the nature of our case, we might choose to compile this in different ways. If there's a small number of choices, then we might simply test sequentially against them. If there's a dense range of values, for example, an enumeration, and we're using every case in the enumeration, then a jump table might be an ideal implementation. We can just use the value associated with the enumeration as an index into a table and jump straight to the case we want, executing the case test in constant time. If we have a range that's not very dense, but we don't have ranges like 3.5, then we can use hashing to take advantage of the lack of density in the range. Finally, if we have a large range and we have things like range labels, then we can use binary search as a fallback technique. Let's check our understanding.